This is a very brief introduction to the history of the Earth for us geotechnical engineers. But somehow, it is important to understand the history if we want to anticipate the future, and that applies also to our soils. So where does it all start? Well, there were many theories about how old the Earth is. Some religious figures assumed that it was in the 1700s, 1800s, assumed that the Earth was about from 6,000 years old. Then scientists began making more precise computations. And for example, Lord Kelvin said, assuming that it all started from a molten state, how long should it have taken for the heat to escape so a crust could form where we could stand today? He computed 20 million years in the middle of the 1800s. By then, Darwin was already proposing his theory of evolution, and he said in order for all these mutations and combinations to take place and the survival of the fittest to emerge from every cycle leading to evolution, 20 million was too short. And this created a profound uncertainty in the community. Geologists began to recognize the fossil record at different excavations of different depths. And so we get to today's conclusions that the Earth is 4.5 billion years old. In fact, the universe started much earlier, like 13.6 billion years earlier. But it took time until all that mass after the Big Bang began congregating and forming the bodies that we find today in the universe. And so if we adopt this as the age of the Earth, then we can begin trying to understand what has happened since then until today. So let's say that this is 3, 2, 1, and this is the present, where we stand today. Well, for the first billion years, it was abiotic. There was no life. And then we really do not know how, but atoms got organized in that very precise structure that gives rise to life. Now, it is so difficult for molecules and atoms to get organized as they are randomly vibrating that probably that happened on a substrate. And so it is very likely that life started on a mineral surface where the atomic activity decreases and molecules get organized. And so there were some hypotheses as the role of clays in the initiation of life. The fact is that once life starts, the atmosphere was primarily a CO2 atmosphere, and life begins capturing CO2 from the atmosphere, converting it into organic chains, and releasing the oxygen. And that was made possible. It requires lots of energy, and it was made possible by the sun. And so the sun, solar energy, was the fuel that converted the atmosphere from a reducing atmosphere to an oxidizing atmosphere through photosynthesis. Now, this is so critical, not only because our existence is life itself, but it is so critical from a geological point of view because until this moment, there were no oxides. There were no carbonates. So oxides, carbonates of biological origin really begin taking place in this period. And then more complex forms of life begin taking place. And eventually we reach to this period here, the last 500 million years, where the Jurassic period, for example, takes place, where there were all these very advanced and organized matter, and that matter, so much biological activity begins getting trapped in the subsurface. And so this is the period where we form coal, oil, and gas. So look, folks, how important this is to understand our situation today. We trap the CO2 from the atmosphere, and bioactivity converted inorganic carbon into organic matter, release oxygen into the atmosphere became oxidizing, more complex forms of life developed, and then, still fueled by the energy of the sun, all this bioactivity eventually got trapped, forming coal, oil, and gas. Therefore, the fossil fuels is a chemical battery that is storing solar energy, and it did it through 300, 500 million years. Now, the many other fascinating things begin happening at this very end. For example, and this is 1 billion years, if I expand this scale a lot, and I just look at the last 50 million years, that is where we see lots of continental activity, and then, for example, the Red Sea begins opening up around 25 million years ago. Just here, in this very final end of the story, is when much of the geological features that we see today developed, and it's still moving pretty much at the rate that our nails grow, 20 millimeters per year or so, like many other tectonic activities moving at that rate. But then if we zoom in much more, so I need to see really the detail here, so I'm going to multiply by 1,000,000 times. So if we do that on this new scale, and now let's say that we have the last couple of thousand years, and we see lots of our social activity and human activity beginning to have significant effect on the environment, and that really takes off. So this is where we are today, during the Industrial Revolution, in just the last 200 years. So if this is 1,000 years, in the last 200 years, we realized that water expansion to form steam is so pronounced, by the way, 1,700 times, that was a great way of creating energy, converting energy, and that became the steam engine. And that was the beginning of what ended up being the Industrial Revolution. And we started by burning coal and then oil and more recently gas, but we began burning the fossil fuels here at the end, so it gave rise, by the time we burned these long organic molecules becoming very long to very short, methane being CH4 here. Anyway, when we burn them, we recombine them with oxygen, we release the CO2 into the atmosphere, and this is the growth of CO2 in the atmosphere since the Industrial Revolution, and together with that, there is an increase in temperature. And you may wonder why, because the atmosphere is here, and in fact is thinner than that line. If this is the radius of the Earth, let's say 6,400 kilometers, the atmosphere is only 10, 12 kilometers. So we are taking all that CO2 and we are releasing it on very thin skin, thinner than the line, and that is where all the thermal balance of the Earth takes place because of this greenhouse effect when the solar rays get trapped. In the meantime, we have other sources of energy. We have solar energy itself through photovoltaics, and then the solar and the rotation of the Earth creates tides. We can use tides, and the sun and the relative heating of the different parts of the surface promotes wind, and we have eolic energy, wind turbines. And because the sun evaporates water and the water gets carried away and precipitates near mountains and give us the fluvial energy, we have hydroelectric. So all the sources of energy that we count on, and by the way, we count on these at the order of about 85% of all the energy that gets consumed in the world, all that energy is stored solar energy, wind, solar, hydroelectric, tidal is a stored solar energy. And so there are a couple that are also making a mark, which is geothermal. And geothermal has great potential. If you compute the geothermal gradient of the Earth, which is, let's say, 25 degrees Celsius per kilometer, as soon as you go down, let's say 40 kilometers, you're at 1,000 degrees Celsius. And so 40 kilometers is also a very thin shell in this volume, and the rest of the Earth is hotter than 1,000 degrees Celsius. So we have a huge amount of geothermal energy. And finally, we have nuclear. And by the way, that was the big mistake that Lord Kelvin did. He thought that all the energy that was trapped in geothermal was because of the attrition friction that was taking place during the formation of the Earth. However, there is an internal generator of energy, which is radioactive energy in the Earth, which is keeping it hot. But if we discard, or if we leave aside for a second nuclear energy and geothermal, which are small components of the total energy that we consume in the world, it is all about solar energy. In conclusion, this brief history of the Earth allows us to understand so much about the challenges, about what we have today from a geological point of view, and about the challenges that we face as we move forward. We have converted an atmosphere from reducing to oxidizing. We have changed the minerals. We have trapped energy, and we are consuming that stored energy, now altering the atmosphere.